Okay, thank you very much, Jennifer. I want to begin by thanking my co-authors listed here. We partner primarily with the Tampa Bay Estuary Program and more than 20 other collaborators across these 8 agencies and institutions. So in Tampa Bay, we have several local drivers of acidification. This map here in the top right shows land use in the Tampa Bay watershed, where urban is in red, mining is in purple, and agricultural is in yellow. We have 4 major rivers that deliver low pH, high CO2 waters and nutrients from this 2,200 square mile watershed. We have periodic algal blooms that can increase pH, but also cause post-bloom acidification events. Much of Florida, including Tampa Bay, as you know, sits on carbonate bedrock and sediments that can dissolve during low pH conditions. So despite the extensive urbanization throughout the watershed, Tampa Bay has more than 40,000 acres of seagrass around its perimeter, which is shown here in green on the map. And this seagrass affects pH and CO2 through photosynthesis and respiration. So next slide, please. Perfect. Ocean acidification is a global problem driven by elevated atmospheric CO2 due to the burning of fossil fuels, land use practices, and cement production, and is therefore very difficult to manage on a local level. It occurs as excess CO2 in the atmosphere is absorbed at the surface of the ocean, where it combines with water to create a weak, naturally occurring acid called carbonic acid. This acid decreases water pH and reduces the concentration of carbonate ions, which are important building blocks for shellfish and corals to make their shells and skeletons. So we refer to these chemical reactions you see here as carbonate chemistry. Now, in addition to ocean acidification, coastal acidification is driven by the same types of chemical reactions caused by local and regional processes such as eutrophication due to nutrient pollution, as well as upwelling and freshwater inflow, both of which deliver low pH waters and high CO2 waters to these coastal zones. This can be addressed by local and regional management practices. So next slide, please. Tampa Bay is a success story with respect to water quality and seagrass restoration. Nitrogen loads to Tampa Bay in the top graph were actually at their highest levels back in the 70s and early 80s, which caused frequent algal blooms and loss of seagrass throughout the bay. These loads thankfully have decreased through time through the implementation of a successful decades-long nitrogen management strategy by the local community and the Tampa Bay Estuary Program. As a result, we've been able to restore seagrass coverage back to 1950s levels. The white and red circles on the bottom graph shows mean monthly pH in the bay, and the green bars show seagrass acreage over the same time period. When nitrogen levels were high and caused the eutrophication, algal blooms caused extreme highs and lows in pH during and after the algal blooms, so you can see on the left of that graph. As nitrogen loads and algal blooms decreased, pH in the bay began to stabilize, and you can see that pH has increased over the years as seagrass has been restored. So one of our primary objectives in Tampa Bay is to examine the role of nitrogen management strategies and seagrass restoration in buffering acidification as a restoration benefit. We see evidence for this, but the historical data are only these daytime measurements, and we need higher resolution pH and CO2 data to better examine acidification chemistry and figure out the processes controlling it. Next slide, please. And here is why. Recent studies indicate that photosynthesis during the day in seagrass beds can locally elevate pH and decrease CO2 and may provide some protection from acidification for marine species like shellfish. But also, conversely, respiration at night can decrease pH and increase CO2. The ability of seagrass to buffer pH depends on the balance between this photosynthesis and respiration, also how close you are to the seagrass bed, and the speed and direction of the water that's flowing over the seagrass bed. Okay, next slide, please. So in 2015, we conducted a pilot study to examine carbonate chemistry in seagrass beds more closely to inform the development of our acidification research and monitoring approach in Tampa Bay. We established sampling transects inside and outside of seagrass beds in end-member bay environments in the upper and lower Tampa Bay, that it contained percent carbonate sediments ranging from low to high percentages, and water mass residency times. There were measured spatial and temporal variability of the carbonate system along these transects to examine the biological and physical controls on the water chemistry. Some of our key findings were that seagrass can locally increase or decrease pH by up to half a unit and PCO2 by greater than 500 microatmospheres. We also found that we have very high spatial and diurnal variability, strong tide and water mass residence time control with longer water mass residence time amplifying these chemical signatures. And we also saw evidence for calcification and dissolution in the seagrass beds. Next slide, please. Here we go. This is an example of our pilot study results for pH on the top, PCO2 in the middle, and total alkalinity on the bottom, where our upper Tampa Bay graph results are on the left and the lower Tampa Bay results are on the right. Each line shows concurrent measurements along a transect from dense seagrass to bare sand at a specific time of day, with the blue colors indicating nighttime measurements and the red colors indicating daytime measurements. You can see the effect of seagrass photosynthesis and respiration on pH and PCO2 during the day and night. We're particularly interested in carbonate dissolution because it sequesters that CO2 as bicarbonate and also buffers against acidification. This can happen in the seagrass beds through a process we call the bicarbonate pathway. Basically, as carbonate dissolves, total alkalinity increases. So we can use total alkalinity to estimate calcification and dissolution. In the bottom right graph, you can see in lower Tampa Bay, where there is a higher percentage of carbonate sediments, we have strong dissolution signature with a higher total alkalinity at night, particularly in the seagrass. We see this when pH is less than approximately 7.9 and PCO2 is greater than 600 microatmospheres. So our next question became, is there a Baywide benefit from photosynthesis and dissolution? And if so, where should we monitor that? So next slide, please. Thank you. We developed and deployed a sensor package in lower middle Tampa Bay on a USF port station in late 2017. This location is part of the bay that's relatively shallow, very well mixed, tidally influenced, and located on bare sand bottom that's more than 2 kilometers from the nearest seagrass bed. Our goal here was to capture a mixed bay water chemistry signature on an outgoing tide and a Gulf of Mexico water chemistry signature on an incoming tide. We placed a second sensor package nearly 60 nautical miles offshore in the Gulf of Mexico, also on a USF buoy, in late 2018 as an offshore reference site. Both collect hourly pH, salinity, temperature, dissolved oxygen, CO2, and light measurements from these sensors. And we visit these sites approximately monthly to quarterly to collect discrete measurements for total alkalinity, total carbon, and pH to validate this sensor data. Next slide, please. These are the results from our first 2.5 years of sensor data, with Tampa Bay data in black and Gulf of Mexico data in red. We see much greater diurnal and short-term variability in the bay, as we might expect. There are distinct differences between Bay and Gulf of Mexico salinity and PCO2 values, which provide good end members to help us distinguish between the Bay and Gulf of Mexico chemical signatures. The dotted lines you see on the pH and PCO2 graphs show that approximately 30% of our data falls below a pH of 7.9 and above a PCO2 of 600, which is when we typically see evidence of carbonate dissolution. Exposure to these more acidic conditions occurs primarily during the wet season, which is likely due to river water influence. The red text on the right of this slide shows a very low range of river pH that flows into Tampa Bay, which is as low as 6.7, relative to the mean Bay and Gulf of Mexico pHs of 7.9 and 8.1 respectively. Next slide, please. Okay, our Tampa Bay sensor sits between the inflow from 2 of the 4 major rivers in Tampa Bay, which is a bit closer to Little Manatee River than the Manatee River, as you can see on that graph or that photo on the left. This top graph shows sensor salinity data in gray, plotted along with daily mean river discharge from both of those rivers in black and precipitation in blue. We have a distinct wet season in Tampa Bay from mid-May to October and a dry season from November to mid-May. And this is reflected in our salinity data. The bottom graph shows a good linear relationship between daily mean salinity from our sensor data and cumulative river discharge, indicating that salinity at our monitoring site is strongly influenced by these two rivers. Next slide, please. So with this data, we perform correlation analysis on our dry season and wet season sensor data to help identify controls on the water chemistry. These graphs show correlations of pH, PCO2, dissolved oxygen with temperature in the pink columns, salinity in the blue columns, and among each other in the green columns. The dry season data on the left, we see strong correlation of all three of those variables with temperature, a very weak correlation with salinity, and a strong correlation among pH, PCO2, and dissolved oxygen, which hints at biological control. But all three of these variables are very temperature dependent. During the wet season on the right, we see only a weak to moderate correlation of all three variables with temperature, a very weak correlation with salinity, and strong correlation among pH, CO2, and dissolved oxygen, which indicates a strong biological control from photosynthesis and respiration. Next slide, please. So a simple approach to try to further tease out the biological signature and potential for Baywide effects. We also filtered this data by high and low tide, day and nighttime, high tide day and nighttime, low tide day and nighttime, daytime high and low tide, and nighttime high and low tide, and then tested for significant differences between the means for these paired environmental conditions for dissolved oxygen, which is on the top, PCO2, which is in the middle, and pH, which is on the bottom. Means for these variables were significantly different for all paired conditions, except for those highlighted in pink. Green highlights show that when we have higher mean pH, dissolved oxygen, and lower mean PCO2 during either the low tide or daytime, we see the highest pH and dissolved oxygen and the lowest PCO2 during the daytime at low tide, suggesting that we do see some benefit from bay photosynthesis at this location. Next slide, please. So remember the discrete data that we collect in addition to these in situ sensors. We examined that discrete validation data to identify potential Gulf of Mexico and river influences on that data. These graphs show our discrete total alkalinity and total carbon data for Tampa Bay during the dry season in black circles and the wet season in red circles. The graph on the right is zoomed in on the small box in the left graph there. The red and black lines show M-member mixing zones between mean Gulf of Mexico and mean river total alkalinity and total carbon for the wet season and dry seasons, respectively. Data would typically fall along these lines or between these lines if it were affected primarily by mixing of Gulf of Mexico and river water. But as you can see, much of our data falls well outside of this mixing zone, indicating that these variables are also influenced by other processes. Next slide, please. The graph on the left shows salinity normalized total alkalinity and total carbon covary predictably in response to photosynthesis, respiration, calcification, and dissolution. Data that is only affected by photosynthesis and respiration falls on a line with a near zero slope. And this the slope approaches 2 when calcification and dissolution are among the dominant processes. With this, you can estimate the ratio of net ecosystem calcification to net ecosystem production from the slope of from a linear regression of the data. The middle graph shows our salinity normalized discrete total alkalinity and total carbon data for the dry and wet season and high and low tide. We have a good linear fit and net ecosystem to net ecosystem calcification to net ecosystem production of less than 1, indicating a strong biological influence from photosynthesis and respiration, but also some influence from calcification and dissolution, particularly during the wet season and low tide, when we have higher NEC to NEP ratios. These results essentially provide additional evidence that photosynthesis and carbonate dissolution may also help buffer pH and acidification in the bay. Okay, next slide, please. So to summarize, pH has increased in Tampa Bay as seagrass has been restored, which can help buffer acidification through photosynthesis. Our pilot studies in 2015 show evidence for local benefit from seagrass photosynthesis and carbonate dissolution. Our sensor data since late 2017 indicate that exposure to low pH and high PCO2 acidification conditions primarily during the wet season. Photosynthesis, respiration, calcification, and dissolution are primary influences on the bay's carbonate system. And lastly, our results provide further evidence that photosynthesis and carbonate dissolution do help mitigate low pH conditions in Tampa Bay. So thank you very much, and I'll take questions if we have time. What are the causes of calcification in seagrass beds?
Leave it on.
Essentially, I'm reading what are the causes of calcification of seagrass beds. Essentially, the supersaturation of calcium carbonate, which occurs mainly during that higher water mass residence time and when it's very sunny out. Those conditions are usually the conditions in seagrass bed that create calcification, or the conditions for calcification by those organisms. All right. What grasses are seagrasses? Eelgrass. How did Piney Point disaster influence the grass's salinity and pH? Okay, so that's a couple-parter. Seagrasses, you can think of seagrasses as literally grasses that grow underwater, and that occurs in freshwater and saltwater. And in Tampa Bay, that'd be an estuary, so that's a mixture of them both. The Piney Point disaster, I'm probably not at liberty to discuss the results of the Piney Point disaster, as we didn't necessarily monitor that. And I don't know if it influenced seagrasses, but I doubt it influenced salinity very much. But we know for sure that it did influence pH because it was in part partially responsible for the algal bloom that was observed in Tampa Bay. And in the beginning of my presentation, I showed how algal blooms really affect pH. In the beginning of an algal bloom, pH goes up, and a lot of people think that's great. And then the aftermath of the algal bloom creates acidification conditions where pH decreases for a substantial amount of time, and that has a lot of negative impacts to the ecosystem. Okay. Are there, I don't have a question, but thank you. Oh, thank you very much. Are any particular species of seagrasses better at combating acidification, to prioritize which species to restore? So it is my understanding that restoring seagrasses in an estuary are fairly difficult as is. So whatever really takes is a good thing. I know in Tampa Bay, at least, there's 3 major kinds of seagrasses, and I imagine restoration efforts try to replant what was already there. How are these results affected by algal blooms? That's a great question. Some of our future work will be taking that normalized total alkalinity and TCO2 total carbon data, and we're hoping to apply that to past algal bloom data that we have and see just how the bay responds with respect to total alkalinity and total carbon with the historical data we have surrounding known algal bloom events. Hopefully that answers your question.
And unfortunately, we're running short on time. So if you could
Excellent.
make this the last question, and the rest, we encourage you all. We're going to put Christopher Moore's email and chat, and you can respond to him directly with your questions. But Christopher, if you
Please
could
do.
just take one last one.
Okay, the last one I see on the right. How do you predict increasing storm runoff will affect these relationships? So in Tampa Bay, there's 4 major rivers that deliver fresh water to the bay, and the Little Manatee and the Manitou rivers are the ones that affect the monitoring location, but in fact, the Hillsborough and the Alafia rivers deliver much more water to Tampa Bay. And I believe combined, those 4 rivers far outweigh the stormwater runoff that we necessarily be able to see in our data. But stormwater runoff does usually carry a lot of bad things for water quality. So stormwater runoff could still affect these relationships. It'd be a wonder to figure out how. So thank you very much, Jennifer.